Okay, great. I'm Cameron Davidson-Pilon. I'm here at our headquarters in Waterloo, Canada. It's near Toronto, if you know Toronto. It's only 3 p.m. here. I wish it was later. I could join you for a beer. I'd love that, but it's too early. It's still work day. But I'm the co-founder and CEO of Pioreactor. And what do we do? We make biotech hardware. It's me, myself. My background is software engineering and statistics mainly, and computers and math and all that. And my partner, Evan Polito, uh, generous background in electrical engineering. Um, Neither one of us is a mechanical engineer, and you'll maybe start to see that in our products. Um, so we're coming at it from a very like interesting angle, this problem. Like I said, we make biotech hardware. Specifically, we make bioreactors, and these bioreactors use Raspberry Pis and Linux. That's kind of interesting. So, your next question is probably, what is a bioreactor? If you have been to a microbrewery or any brewery for that matter, you've probably seen tanks like this in the background. That's a bioreactor. This is a bioreactor. This is a very expensive looking piece of scientific equipment that is typically reserved for microbiologists. Um, this is our bioreactor. It looks a little bit different. It's much smaller. Um, but bioreactors are used for many, many different things, food and nutrients. A classic example that I use is like vitamin C and citric acid. Both those are produced in bioreactors via fermentation by bacteria. We extract it and put it in our food products. There's lots more, but that's, two common ingredients. Pharmaceuticals use bioreactors. Beer and wine, of course, we're familiar with. Plastics, I'll get more into that, but some plastics are created via fermentation in bioreactors. Wastewater treatment plants use bioreactors. They're just really big puddles of bioreactor material. Uh, Cosmetics, biofuels as well, and research as well. So lots of use cases for bioreactors. It's a very general term, bioreactors. Uh, another example, I have some raised garden beds in our backyard here. And technically, a raised garden bed is a bioreactor. You're maintaining soil cultures and microbial cultures in that raised garden bed. So bioreactors are very general. We focus on our product on the last use case, so research. We're not growing beer or plastics or fuels. We're just focusing on the research of microbes in a bioreactor. So we sell this bioreactor. We sell it internationally. For the UK crowd, it's like 235 pounds. Um, it's the nice thing, the very different thing about our product as well is that there's no email us for a quote, which you'll often see with scientific equipment. It's just, here's our product. You have a credit card, great, go ahead and buy it. You don't need to contact us to talk to a salesperson. It's all very transparent pricing that way. Um, we actually sell this as a kit as well. So you assemble it yourself. And we like that idea. We want people to understand what they're building. I'm talking to builders and makers in this audience, so I think you kind of get the idea. We take a lot of inspiration from companies like Prusa printers. We like that idea of like kits and upgradability. We follow that kind of style. Looking at the kind of kit, a lot of these parts are 3D printed too in-house at our headquarters. So everything kind of labeled or marked that these are all 3D printed. We use a combination of PLA and polycarbonate, carbon fiber, if you're familiar with 3D printing. Um, the nice thing about the latter plastic, this PCCF, we call it, is that it's autoclavable, which is really important for biological equipment. You need to like get the materials or the compartments very hot to sterilize them. So we need a plastic that can withstand very hot temperatures, like 125 C temperatures. Um, I can talk more about that later. But yeah, so we 3D print everything in-house. We have a big printer farm here. We assemble the components and we ship it as a kit. to our end users. Uh, who buys our bioreactors? Researchers do at universities, startups do because it's an easy and cheap way to sort of scale out and try different things before committing to like one different or one specific idea. High schools do. In fact, this was like a high school group, I believe in Spain or Portugal. I think it's Portugal because that's a Brazil shirt. Um, and it's not Brazil, so it must be Portugal. Um, so this is actually a picture of a group in the UK, I think Birmingham. They bought 20 from us a while back, and this is them proudly in front of their cluster. I'll talk about clusters later. We actually have one foreign distributor, and they're based in the UK, and that's Labcrafter. They're based in Wales, I believe, and they sell lots of great open source scientific equipment, including our bioreactor. So if you're interested in this product, go check them out because it's much easier to get the product to you if you're already UK based. Um, and they also have like transparent pricing, and they're a great team at Labcrafter. Okay, so getting to more specifics, I mean, I have the bioreactor here. This is the 20 ml version I'm showing on screen. My camera has the 40 ml version. It's just taller than the 20 ml version, but you know, it's tiny, right? It's not very big. It's enough for research, but not enough for a pint. Um, this is like the vial that comes with it, a small glass vial. There's a little stir bar in there. So not very big, and you can kind of see why I call it a hat. Technically, it is a hat for a Raspberry Pi. It's the hardware is on top, the wetware is on top. The entire thing is just on top of a Raspberry Pi, um, which has issues, and we'll get into that later in products. Um, but this is kind of what it looks like, and we have the Raspberry Pi in the bottom, of course, and our custom hardware on top. Um, just going to move my yes. Okay. So I'm just going to label some important parts. There's like a DC fan with a very simple like computer 40 millimeter computer DC fan with some magnets attached to it. Um, and why do I have that? There's like a little stir bar, like I said, inside this glass vial. So as that fan turns, the stir bar turns, and you get mixing. Um, Outside, or I can control mixing outside without touching anything internally. We have a little PCB with a resistive load on it. That's for heating and temperature control. Microbes like a very consistent, 30C or 37C or 45C. So we can provide that to the microbes. Of course, there's the hat with GPIO pins and sensors. Um, I can talk more about that later. And even on that hat, there's an RP2040. So we're kind of all in on the Raspberry Pi ecosystem. That RP2040 controls some of the motors and LEDs on the device. It's just easier to use that than using. There's also like an ADC on it. Easier to use that than using some other hardware. And then we have these optical density sensors, and that's kind of what makes this product really interesting to a lot of researchers. I'll talk more about what optical density is. So what is optical density? One of the questions I used to think about when I was younger is like, what does a bucket or a pail or container of bacteria look like, right? Like, what's if I were to just like scoop up a bunch of bacteria, what's going on in there? And I've partially answered that by building this product. It kind of just looks like a cloudy liquid. And the proper name for cloudy is turbid or turbidity. So as the bacteria grows over time, it starts to scatter more light. And you can measure that amount of scatter, uh, turbidity, and then we call that optical density. So this is some data we backed out from our Pioreactors. Um, Kind of focus on the bottom left here, those OD readings, optical density readings. As the culture grows, we can track that over time by using this idea of scatter, of light scatter as the culture gets more dense. And this is just like kind of what it looks like in operation. It just looks like a cloudy liquid. So Formally, what's going on is this is a top level view. If I cut the Pioreactor in half, we shoot in uh, IR infrared LED, like light into the culture, into the vial. Most of that light passes right through. Some of that light will detect or strike a cell and scatter. Um, and some of it will scatter 90 degrees, some of it will scatter elsewhere, but the ones that scatter 90 degrees will capture in a photodiode, which measures or is sensitive to the IR light. With a second photodiode as well that measures a reference, or it's not measuring scatter of the culture. It's just measuring. It's this bottom one. Oops, it's this bottom one, bottom to the right. That just measures how much light is being emitted by the LED, and it's a reference. It's a normalization factor that we need because some LEDs will like dim over time, or their intensity will change with temperature. So we want some sort of reference to measure that. Um, what that looks like on the device, it's two almost identical PCBs that have a very small photodiode on there and some amplifiers and ADCs on the board as well. Um, this device, this board, like we created, it's called the iSpy. It's STEMMA compatible. STEMMA also known as Quick, I think. It's like a protocol that Adafruit has sort of established. We really like that protocol. It's nice. STEMMA is a very easy, user-friendly kind of system. So we've sort of developed our sensors around this sort of STEMMA environment. So these are all fully STEMMA compatible, and we'll talk more about that later. The STEMMA thing. So what's the tech stack actually look like? Like getting less into the hardware, more into the software. Um, we're using tools like the Raspberry Pi OS. So that's like our default kind of image that we'll modify. Um, our sort of core software is Python. We use SQLite 3 as a database. Our front end, our UI is all React, hosted by Light HTTP, Flask, and Huey. We use Avahi for some network communications. OpenOCD flashes the RP2040, systemd and Mosquito just for other like communication and well, systemd for startup protocols and stuff. Um, we use actually, yeah, talking more about MQTT, we use that for uh, inter and intra device communication. So um, we use MQTT for processes to talk to different processes. We use MQTT for machines to talk to different machines. So it's used all over as kind of this overarching data bus that we can like move data back and forth between machines. And so why do we want to move data between machines? Typically, you won't buy one bioreactor for research. You'll buy many bioreactors because you want to be able to do trials. You want to experiment with some parameter over a range of conditions, or you want to do replicates. You need, like 3 replicates per environment. Um, so we had this idea of clusters, and for if you have a cluster, you kind of want at least, or you want one of them to be some sort of like leader or orchestrator. We call them leaders. In our case, that leader hosts the database. It hosts the web UI, so the web server. It's kind of what you talk to, and that machine talks to all the other machines, all the other Pi reactors. So we have this like leader worker distinction. The leader can be like the worker being like, I'm actually going to run stirring, I'm going to run heating, I'm going to collect data. So the leader is a worker and the workers are workers. Kind of formally, it looks like this. We have a leader worker and they talk to different workers. Uh, how do they talk to each other? Over HTTP. So each Pi reactor is a Raspberry Pi and they're all connected to this main leader, and they all have a web server and they're all talking to each other over HTTP, simple like web UI calls or web API calls. So if you squint and you kind of sort of close your eyes and think about this and just like just sort of take a step back, you know what am I talking about? I'm talking about each Pioreactor has a web server and HTTP and clusters, and I'm drawing these sort of database diagrams, these like circle things, and oops, we've all become sysadmins now. Like what happens is a user will, collect 6 or 12 or 10 of these, and they've effectively created a small cloud environment in their little lab. They're technically sysadmins, right? Like I don't want them to be, but they kind of have to be sometimes, um, which is fine. Like we've built kind of abstractions on top of the Raspberry Pi that make it easier for them to use the Raspberry Pi to talk to different units. Um, they're not running, firewall protection stuff. They're not. Well, sometimes they're plugging in Ethernet, and sometimes they're like SSHing in, but that's rare. That's kind of the exception when they have to do that, or they're kind of like going off script, and that's totally fine. But yeah, we've essentially shipped a small cluster of compute to them via networks, and they're kind of like they're a sysadmin. So I will switch to actually showing off this UI, kind of how it works and how to control a cluster of Pioreactors. Um, XR1. So we have like a demo cluster that we use. Just gonna move some things so I can see my screen. Okay. Okay, so this is right now, like I'm connected, if you saw my URL, xr1.local, xr1 just the name of the computer. So this is like a Raspberry Pi on our network, and I have 4 Raspberry Pis in this cluster. There's some network information. You can from this kind of screen, you can add new Pioreactors. Um, you can like control Pioreactors. You can identify them. It's called run like hardware tests to make sure your Pioreactor is working. That's like really important after you install or you assemble it. You want to run a self test to make sure the pipes all work. Um, from this main page, you can control Pioreactors too. So like for example, you can start stirring and you can't see it, but there's a Pioreactor that has a little stir bar that's stirring. Um, you can start stirring on all of them if you wanted. I mentioned optical density earlier. We can start optical density on all of them. Um, you can, change the RPM. There's like feedback loops or feedback, yeah, loops controlled by sensors on the device that let you like measure RPM, measure temperature, measure OD. Um, I didn't mention it, but you can also add pumps as well to the system, like liquid handling pumps, and that's very useful for like adding feed, like new media, adding new liquid into your culture and removing liquid from your culture. That way you can kind of keep your culture in a constant state. They're constantly feeding your culture. That's very, very useful for research. You can use pumps to like add toxins in to see how the culture will react to different toxins like uh, 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 high concentration salts or antibiotics or whatever. So you can do more interesting things with pumps. Um, we collect logs and we display the logs for users. Um, there's the overview, of course. We can kind of see data come in. This is very messy. This is my dev cluster. There's nothing actually going on in this cluster. It's just kind of water, I believe, in the vials. Um, we can sort of start temperature. We can control the temperature on these things and get temperature in real time or whatever. So you're basically like controlling a bioreactor from this UI, and this UI lives on the Raspberry Pi. Um, Other cool things like because we are putting our bioreactors on a microcomputer and not say a microcontroller, we have more flexibility with things like plugins. Like the community has created sort of, and we ourselves have created plugins that make that sort of extend the bioreactor without us kind of providing it out of the box. It's too complicated out of the box, or it's not used, it's too niche out of the box. So we have plugins, a plugin system where users can kind of create their own plugins. So we have some rich plugins here for interacting with like different hardware or different cloud providers. There's like a Slack and Discord plugin for sending logs to group Slacks and Discord. Lots of cool stuff like that. Of course, you can export your data, you know, to CSVs or whatever. There's a rich set of calibrations too. So you want to like calibrate hardware or calibrate to an external sensor as well. You can do that via this system. Um, Configuration is just, it's a .ini file where you can kind of change specific configurations. Um, One thing that I think is underrated that people don't use enough is profiles. Maybe these are too complicated for users, but this is like automations on top of automations, which is kind of like a software engineer's dream. Uh, you can like via YAML, which is its own issue. You can kind of create automations, like you can headlessly control your bioreactor without you having to use this UI. Um, and that's really nice. There's a demo external example. That's nice. Often with bio research, things happen like every 6 hours or 12 hours or 24 hours. You kind of need to be there for that whole duration. And no one wants to be in a lab at 3 a.m. or whatever. So you can kind of create a automation to do something at 3 a.m. as like to sort of solve that issue. Um, I think automations are like really cool, really powerful. It's sort of like a rich kind of expressive pseudo language via YAML to sort of express what you want to do. Um, Anyways, I think yeah, profiles are really cool, but they're underused. Um, and then again, because we're on like a Raspberry Pi system, doing things like updates are pretty easy. You can update over the internet or over like a zip file. It's a bit easier to do it on a Raspberry Pi versus like a microcontroller. You can do it on microcontroller, but it's just more work. It's very easy on a Raspberry Pi to sort of have these kind of updates. Um, One last thing I kind of show you, like, we have this really cool solo diagram. This is nice for schools, like for education, where like a group of students might have one bioreactor in front of them, and they're using this UI to kind of control it. So they're not messing with other people's bioreactors. They can see just theirs. Let me jump back to slides. So how do we actually build our custom images? Um, we take the raw images, they're not raw, but we take the images from raspberrypi.com. We use the light OS image. Um, we apply this, we sort of put it through our pipeline. It's Emu versus or via Custopizer. Um, Custopizer is a project done by the Octoprint developers. So Gina, aka Fuzel, basically maintains this, and it's great. It's a really easy way I can basically just like write a bunch of Bash scripts that execute against a static image. This all runs like on my laptop or in a cloud environment, and at the end of that pipeline, I have a reproducible image that I can ship to end users. I know exactly how it was built, and I can test it and I can, debug it very easily. And there's no like the nice thing is I don't have to log in and like add a SSH key or there's no like modifying the image beforehand. There's no human intervention beforehand. Uh, some open questions we're unsure about. We've been at this for 3 or 4 years. Um, and there's still some things that we're not sure how to do, or the tools haven't really caught up to what we want to be doing. The first is like, how do we serve HTTPS on a local network? There are tools, like I've seen make cert, MK cert, uh, and that it's a really cool. It's like Makedir, but make cert, make certificate. It's a cool project, but it still requires the end user to add the certificate to their browser, their Chrome browser or Firefox browser, which is not a very pleasant or user-friendly experience. Even I feel weird adding a certificate to my browser. I can't imagine like a biologist wanting to do that. Is this thing hacking me? They might be thinking. So it's still not clear if it will ever be possible how to do HTTPS on a local network easily out of the box. It probably will never be, but like how do we kind of approximate it would be nice. Because if we can do HTTPS, we can do things like um, user accounts and admin accounts and things like that. Right now, we can't do that because we can't really keep passwords because it's all over HTTP. Um, and how do we make the zero conf experience better? Right now, like I said, we use like a network to connect the Pioreactors. Um, that often requires like a separate network to host it, whether it be like a Wi-Fi network from a router in the institution or building, or like an Ethernet network. Um, I would love a more sensible zero conf experience for users that says like connects Ethernet between bioreactors and that goes straight to your computer and everything just works. It's still very complicated between like OSs like Windows, Linux, Mac. It's just never like a very clean experience. One hack that we have previously done is to host the Wi-Fi on the leader Pioreactor as like a local hotspot. Um, it's a hack, and there's nothing more permanent than a hack. So we still kind of suggest that. It's not a great experience. You have to change their Wi-Fi settings to get to this UI. Anyways, that's something we're still like fighting with is this network zero conf experience. Um, and the last question is like, what will Raspberry Pi SBCs look like in 10 years? Like, there's a trend for faster CPUs and moderately more RAM from the Raspberry Pi Foundation, but we actually don't need faster CPUs or more RAM. Like in fact, the RPi Zero 2 is sufficient. Like we don't need that. Like that has enough RAM for what we need. Has enough CPU for our workloads. Um, but like the Raspberry Pi 2W, Raspberry Pi Zero 2, um, the form factor is not perfect. There's no Ethernet, there's no USB, USB B, or A. So it's not like the greatest form factor. In 10 years, will they still be producing like a cheap and moderately CPU capable board? I kind of hope so, because like a lot of applications don't need, that much compute power or that much RAM like us. Maybe there's some other provider that can kind of come in and do that. I know like they're like the Raspberry Pi 4s are great right now, and they'll be in production for a while, but kind of what comes after that. Um, so yeah, open questions around where does Raspberry Pi put us in 10 years? And then what's next for us? So we have a new hat we're working on called the V2. This will have USB-C power delivery on the hat, and that'll back power the Pi. So that'll it gives us more power for the peripherals, like the motors and the LEDs and the heater, um, and lets us power the Pi without separate power cables. Uh, Reversible motors are coming as well, and this allows users to change the direction of liquids so they can kind of like put liquids in and then sort of change direction of the liquids to go out again. Um, Doubling down on STEMMA QT. STEMMA QT is great. It's fun. We have like a bunch of like compatible STEMMA QT sensors by Adafruit that stick right on. I don't have any here with me, but like there's really nice spectrometers and sort of remote temperature sensors that we like. Um, Later on, there'll be like a built-in display, also powered by STEMMA QT, kind of somewhere on the body. And we're actually going to lose the hat portion of this next hat. Um, right now, everything's sort of stacked on the Raspberry Pi. This is, not a very good idea in retrospect. Like any kind of spill or leaks will affect the entire stack. So the future iterations will kind of move the wetware off the entire Raspberry Pi to the side, have better liquid protection controls. But it won't be a hat in the traditional sense anymore. So it'll be more of like a Raspberry Pi powered product. Um, Kind of on that last point, I mean, this is like our third kind of iteration on the Pioreactor. It looked a lot wilder in the first few iterations, like more wires, uglier wires. Um, And I get back to like my point that there was no mechanical engineer on our team when we first started. Um, and that kind of showed in the early products, and we've kind of adopted that as our new aesthetic, this kind of like raw, open, biopunk looking aesthetic where like wires are kind of present, and we're going to keep that idea, that aesthetic. So don't expect this to look anything like an iPhone in 10 years. It'll look always pretty open and raw. Photos of early iterations. I'm looking at the questions. Uh, yes, absolutely. Let me think. Where do I find photos? Um, I'll find some shortly. But yes, anyways, that is, oops, let me go back. Nope, not that. I think that's it. Yes, thank you for listening. Learn more at pioreactor.com. You can email me too. I'll put my email on screen, cam@pioreactor.com. If you have any questions, that UK group was labcrafter.co.uk. Feel free to reach out if you have more questions. We also, a lot of our code and hardware is open source as well. And that's at github.com/Pioreactor. Um, you can kind of see our main repositories and main hardware products there. Cool. So that's it for my presentation. I'm happy to answer questions. I'll try to find some photos of the early iterations as well while we're chatting.
Cool. So I think so. One question I had is whether you can do large scale collaborations across labs. I guess probably not because you're sort of struggling with the HTTPS and all that sort of stuff. So
Um, you can like because it's a Raspberry Pi, you can kind of get Wi-Fi out of the box. So you can send data via like HTTPS, Wi-Fi, or Ethernet or whatever, like out of the
right,
network. That's totally fine. It's more just like when you interact with the UI, that's HTTP.
right,
So I know there's like some groups where they have sort of bioreactors around their offices in different labs and different like levels. I know they kind of centralize their data collection via just like, you know, scrape the data from MQTT or export via the database and push it to a central location. So that probably works at a larger scale too, versus just like a single organization. So yeah, it would definitely work. And then you can also, the cool thing is like one group could kind of develop the plugin, share with other groups, and that kind of like automates all the data collection.
so how does this compare to like a professional setup? Like if you, well, this is a professional setup, obviously, but you know what I mean. It's sort of like a bigger
It's
company.
it's
What sort of things do they sell? And
yeah, it's like a it's a kind of between like the maker professional setup. It's a lot more affordable. It's like at least 10x to 100x cheaper than existing bioreactor, like the nice glass ones and like stainless steel ones. It lacks some sensors, like pH is a very common like measurement you want with bioreactors. We don't have that yet. We have some ideas on how to do it and incorporate that, um, but it's going to be more expensive than the actual unit, unfortunately. Uh, a lot of like larger, more expensive bioreactors have features that are often liabilities. They'll have like very sensitive probes that you don't actually need. They'll have like complicated and excessive dosing ideas. Um, and for a student, they might accidentally break it, and that's a real shame because it's they have to bring in the team or the manufacturer again and get it replaced, and that's a whole ordeal. Um, these, if you break, it's not a big deal, right? Like we sell all these accessories, all these parts as accessories, like replacement parts. You know, um, because it's a kit. If you break it, you tend to know how to build it or reassemble it yourself, repair it yourself. Um, all of the 3D prints are open source as well, so you can just like download a STL and sort of redesign it if you want. Um, So yeah, it's missing sensors, which is sometimes okay, but it's also much more open and accessible than existing solutions, existing like setups.
Yeah, so this must be good in research areas where they want to do a lot of samples all at the same time, and they want to like 10 or 15 or 20 like really expensive reactors just to get started.
Yes, yeah, researchers like it for that reason. Um, they can kind of scale out quickly, horizontally, very fast.
Yeah. Well, I really like your comment about the Pi Zero 2 because it's my favorite Pi as well. Just so much
It's
stuff
great.
is just
Yeah, yeah,
just
yeah.
like real
I
sweet
think it's
spot.
awesome. Yeah, 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 yeah. It's what I recommend to users initially, and then if they need like Ethernet, I might, upgrade them to a Pi 4. Um, but yeah, the zero two is great. It's also
Yeah.
like great for power reasons. Like you're not wasting cycles on powering a USB that you're not using.
Yeah. So I know that Raspberry Pi created a compute module based on the Pi Zero 2, but it's only available in China at the moment.
Oh, okay, interesting.
It seems like a really winning product though. Just like it's got such a nice sweet spot.
Yeah.
Um, so what sort of problems do you get from the users then? Like what sort of like debugging do you have to do for them? Is it mostly just they misunderstanding the instructions, or is it there's actually you have a are they reporting software problems, or what sort of feedback are you getting?
Most often it's networking issues, right? It's why can't my UI load, right? Um, typically they've tried to connect it to like a institution's Wi-Fi, like an educational institution's Wi-Fi,
Okay.
and that's very locked down system. They don't like random Raspberry Pis in the network, so we'll work with them to kind of figure out how to get the network working. Um, I mean, the surface area is very large of our software, and I'll often ship bugs without even realizing it. So software bugs are common, unfortunately. Um, there is the occasional like overflow, and that's why our next design will kind of keep this off the Raspberry Pi. Um, otherwise, like yeah, there's mostly like positive things, I would say. Networking is the big one. That's the one really want to solve in the future is how to make networking much more plug and play.
Yeah, because everything else feels like fairly user friendly, and you've set things up nicely with a nice UI, but the networks is just a bit. It's a lot more difficult for normal users to get their own minds around.
Yes. Yeah,
Yeah,
most users, especially today, are used to like plug in Wi-Fi credentials and you're good to go. Um, but it's not always like that. So
yeah. I mean, it's not rocket science, but it's still a barrier. Yeah.
yes, yes, yeah, yeah.
I don't know if there's other questions in the chat or not. If anyone has they want to
Yeah,
unmute and ask a
can I
question.
just ask you, you're talking about, you don't know where Raspberry Pi is going to be in 10 years, but a lot of us in this group also use ESP32s, which of course have Wi-Fi and MQTT. I use that a lot, but it's got ESP now as well, which is very good for communicating between them. Is it something you've looked at, ESP32s? Yeah, they're very cheap and they're quite capable for low power kind of use cases.
Yeah, it's one of those things that I think early on, um, just by happenstance, we decided to choose Raspberry Pi, and because of that, we've built software and tooling and all that around the Raspberry Pi. So things like the plugin system, the updating system, storing configuration as files, um, communications, like all that's kind of been optimized around the Raspberry Pi. There is a future where we could sort of change and change direction and go to microcontrollers. Um, but that's like a very different design, I feel. It's like it's also what we're not very familiar with after spending 3 or 4 years with the Pi. Like we understand that domain space a lot better. Um, so yeah, like we could definitely check out or like look at the ESP32s again or some sort of equivalent. Um, but it's yeah, it would be like a big changing the entire cruise ship idea. It'd take a long time, is what I'm saying.
Cool. There's a few questions in the chat. I don't know if anyone wants to. unmute, or should we just read the questions?
Yeah,
Yeah, sure. Oh, go ahead. Sorry.
I was going to say, so I think it's a brilliant product you've got there, and clearly you've had a really good journey. Have you had any heard of, or rather yourselves during the development phase, any disasters where something went really left field and
Exploded.
yeah, I wasn't going to go as far as exploded, but it'd be interesting to know. You usually design, from ground up is can be quite challenging.
Oh, failures, or disasters. We've had like pumps malfunction, and they will just if they malfunction, they'll just like, especially like the exit pump, the waste pump we call it. If that fails, the main pump will just keep adding liquid over and over again. And that it's kind of like flooded a whole table of Pioreactors before, which is disappointing. It's like, it's not water, right? It's like a organic, turbid, gross culture. So it's a very like sticky, smelly mess, um, when it does like overflow. Other disasters, I'm trying to think. I mean, in our like 3D printing farm, we've had like just enormous blobs and total failures of like, set a print for the weekend, come back and nothing's been printed. But PLA is like all over the work floor for like 48 hours straight. It's been extruding. Um, yeah, I would say those things. It's been a pretty like okay process. Yeah, I would say so. Yeah, yeah.
No major disasters. The only other thing I was thinking of, again, coming back to your futures and what we've just been talking around ES32, and I see that somebody suggesting the 32 being controlling the bioreactor, which obviously you've got the Pico there, I presumably is
Mhm.
one. But another one maybe is to think about using something where you've used hardware extraction, i.e. something like Proxmox, where you can then virtualize your operating environment, and then that means that you're less reliant on things like pies, because you could actually therefore have a different hardware underneath platform and support different types, but still give the same user experience.
Did you say Poxmox?
Prox,
Pox?
yeah, Proxmox, Proxmox. It's a open source virtualization environment, and there is a version that's available for Pies as well as Intel boxes, as well
Okay.
as I think there's a version for Apple now as well. So that might perhaps give you that future proofing, because if you've migrated to that environment, you then have a level of abstraction that might give you that versatility. And again, for some of the clients you've got where they've got different hardware, they
Mhm.
can utilize that instead. Just a thought.
Yeah, I'll explore that. That's an interesting idea. Yeah, cool. Okay, Proxmox.
Mm.
It's a bit of a design decision, isn't it? Because once you go to Proxmox, you're taking out the possibility of ESP32s and Picos.
No, because you'd have the ESP and Picos running the reactor on the network. And again, it depends on how you design it. But that's the thing, is
But
that
you can't run Proxmox on a Pico, for instance.
no, but you would have the Proxmox running on your Pi or another box. So you would then have where you've got all your front end GUI, that's where that would all still reside.
Yeah.
So it would, because as we were saying, is how long does the Pi potentially live for? Hopefully it'll have isn't it, many more years and whatever,
But you can have a higher cost, as you say, a higher cost higher with Proxmox, but then have $2 ESP32s running your kind of
the reactor, yeah.
yeah.
No, I think you're right. I think that's
How about those
Maybe answer some of the
ESP32?
questions in the chat there. Sort of,
Yeah,
everyone's
there's a good
re-architecting our solution, but
yeah. There's a good question here about eukaryotes versus prokaryotes. You can do both. So the question is like, is it just like bacteria, or can you do like more complex things like um, yeast or algae? And you can do both. It's as long as the cells prefer like a liquid environment, that's fine. Um, the kind of like caveats are mammalian cells are very sensitive to shear forces, so like they don't want to be near the stir bar. Like that kind of RPM is probably too much for the mammalian cells. Insect cells, kind of the same idea. Um, but definitely like algae, bacteria, most bacterias, yeast, even some like filamentous fungi, which are the more traditional mushroom with like the filaments or the hyphae kind of strands. So if you're doing algae, you can also do like illumination. You can add like white LEDs or red LEDs or whatever LEDs you want. There's positions for that to do that. So you can grow many different types of microorganisms. Um, the Another question about your product illustration showed consistent blacks for the various products, making it look impressive. Can you tell us about the finishes, finishing, and photography? The product itself is just like a matte black PLA. That's mostly for optical reasons. We want like a matte finish, a black finish, um, because we don't want stray light or any kind of like, strange optics due to like non-black, non-matte finishes. For photography, we just have a very simple like photo box. It's about like a meter by a meter by a meter, and there's like different sort of like sheets or backgrounds you can put into it, and then we use a phone camera to take photos of it, and then there's some like minimal post processing software that we use. Not too complicated, but uh, we appreciate the compliment about our photography. Um, After the build, how's the final image distribution done? So we host the images on GitHub, and then we recently changed the distribution because Imager changed. The Raspberry Pi Imager changed. So we use the Raspberry Pi, we suggest users use the Raspberry Pi Imager, and I can kind of show you the new workflow. Um, you can see this, I assume, right? We use like we tell users, well, actually I'll show you the docs. That's even better. Um, for this. So we have like docs on how to go through the imager, and they basically paste in this URL which brings up our images, right? So you're familiar with like writing the images in this new V2 manner, Imager V2. We now sort of like occupy the top level spot with our images, and you can choose the version and stuff like that. And that URL links to a JSON, which has a list of all of our GitHub assets, which are the images. And that's been working well. People seem to be fine with this new workflow. Um, any other questions that I missed? Did I miss anything? That's
I was just,
still.
Cameron, I was just asking about, your problems to do with getting through institutional firewalls and HTTPS. I was wondering, would it not be good just to have your own cloud server and to reverse tunnel from the Pioreactors there, and then you can link it all up and deal with your HTTPS. And that would be how typically Internet of Things is dealt with for smart plugs and stuff like that. Have you considered that, or
Yes, partially. Maybe not to the full extent that you're thinking. One of like the I think the hurdle still exists though. It's like getting the Raspberry Pi to talk to any network at at an educational institution is kind of difficult. Let alone talking to the internet, where our cloud service might be.
oh,
If
okay. So
a
they don't necessarily have access to the internet, is that right? They can't
Yeah,
access the website.
yeah, yeah, right.
Oh, okay. Okay.
Yeah.
Yeah. I
If
don't.
you like, yeah, yeah. like a grad student bringing in a unauthorized Raspberry Pi onto campus and trying to plug it into the network, whether they want, to talk to the computer next to it or the internet, that's the challenge connecting to the Pi to like the actual network.
Hmm.
Yeah, CJ mentions institutions require whitelisting, and that's typically how it works. Is like we'll have uh, us and the student or the lab team kind of contact IT, tell them the MAC addresses. They will whitelist the MAC addresses, and then everything works. Um, they might provide like a static IP back. But yeah, so it's typically like a bit of a song and
Oh,
dance with the IT department.
yeah, that's terrible. So I kind of assume students could access Google from their mobile phone over Wi-Fi. If they can do that, then they can deal with other things. If they can't even do that, then yeah, I don't know really.
Half the problem, like the reason why it works on your mobile device or a laptop in an educational institution is it brings up a GUI, like a browser pop up, and you enter your credentials, and it's like the portal system, right? It's
Ah,
like
yeah,
this, yeah.
yeah,
If you're using a headless Raspberry Pi, there is no potential for a GUI to come up.
yeah, yeah,
So it has to be all via like the terminal or all via like configuration without a user typing anything in. So that's the challenge.
yeah. Okay, yeah, I understand.
There's probably like a lot we can do in that user workflow. Even like, shipping not headless images, but headful images that have like a desktop component and users can like plug into the Pioreactor. They can plug in a monitor and a keyboard and kind of interact with the entire device that way. Like that's probably a great idea. We just haven't really explored it. It it's not a great sales pitch to say like, oh yeah, you buy our product, but you also need a monitor, you also need a keyboard, you also need a mouse to use it. So it's that's a hard sell.
No, no, I think the nice thing about it is even, well, for me, I know nothing about biological things. And you can see it's kind of an appealing package, you know, it's an appealing package if you've got a use for it. I wish I had a use for
Yes, yeah.
it.
Yeah.
Have you thought of using the Pi Connect system? It's quite good actually.
I haven't. I heard about that, and yeah, I saw some news about it a while back, but I haven't actually
Yeah, just get the
explored it
full
as an
GUI.
option.
Just register your Raspberry Pi with Pi Connect, and then you can log into your Pi and get the full GUI. So it's quite useful. If you have a small number of
I see.
Pis, it's free,
Yep,
but
yep,
it
yep,
just
yep.
does all the
Interesting.
tunneling for you and stuff like that. So you don't, if you're just sitting at home and you want to log onto your Bioreactor, you can just do that from home.
Cool. Interesting. We've sort of pushed people towards Tailscale as a solution to that, uh, and that works often for them. Tailscale. Um, but yeah, we have no like. I've never tried the Raspberry Pi Connect system, but that would be an alternative. Yeah.
Really
I
quite
use
good.
a scale scale I found was excellent.
Yeah, it's just removes a whole lot of faff. Just sort of, I think they're charging for it after a certain number of Pis. I don't know. Haven't reached the limit yet. But
Probably. Yeah. Yeah.
anyways, that was a really good talk. I really enjoyed that. Really wish you all the luck in developing it further and getting lots of users. 'Cause it looks like a really great idea. So very
Thank you.
unexpected.
Yeah. No, thank you, Richard, for the invite. I really appreciate it. It's nice to talk to other enthusiasts, Raspberry Pi enthusiasts about this. It's a very niche product. Maybe one day you'll have a use for it. Yeah, but thank you very much, everyone.
Cool.